Box and whisker plots. Let's look at comparing them. Here are our learning goals. I can use a box plot to compare two distributions using symmetry, median, IQR, and/or range. And I can determine whether data may be normally distributed by consideration of the symmetry of the box and its whiskers. So let's start off with a given set of data. We've got a set of data here, and we're asked to find Q1, Q2, and Q3, construct a box plot to represent the data, and determine if any outliers are present. So let's start off with the data. The first thing we need to do is put the data in order. Once we've got the data in order, we need to find the Q1, the Q2 or median, and the Q3. So our median is going to be right in the middle of the data. We've got 8 pieces of data, so that means we end up right in the middle, in between 26 and 27. That tells us that our median, Q2, will be equal to 27. Then our Q1 is going to be exactly halfway in between that bottom set of data. So that's halfway in between 21 and 22. So Q1 is equal to 21.5, or 21.5. Q3, going the other direction, we're halfway in between 30 and 32. So that means our Q3 is going to be equal to 31. So we've done part A. We've got our Q1, Q2, and Q3. Now we want to construct a box plot to represent the data. It's easy to find our minimum and our maximum values, so we'd put those on the plot, and then we'd put our Q1, Q2, and Q3. I've gone ahead and created that box plot already down here, and you can see that we've got our 19 is right there, our 35 is at this end, then we've got our 21.5, our 27 median, and our 31 Q3. Now we need to look to see if there are any outliers present to know whether we include all of that data into our box plot. In order to do that, we need our interquartile range. So we start with our IQR, and we remember that that is our Q3 minus our Q1. Our Q3 is 31, our Q1 is 27. 31 minus 27 gives us 4, so our IQR is 4. Now, we're looking at our lower fence. Remember, that's Q1 minus 1.5 times the IQR. So 21.5 minus 1.5 times 4, which is 21.5, minus 6, which is 15.5. So that's our lower fence. That's down here on our graph. So because we're well below the smallest piece of data here at 19, we know that we don't have a lower outlier. Now let's look at the upper limit. This time it's Q3 plus 1.5 times the IQR, which is 31, plus 1.5 times 4, which is 6. So we're at 37. In this case, our data went up to only to 35. 37 is up here, so we're still inside the fence. That tells us that we have no outliers. Remember, the benefits of a box plot are that we can easily calculate the range and the interquartile range. It enables researchers to quickly identify median values, the dispersion of the data, and any signs of skewness. The left-hand whisker, that's the piece over here, illustrates the spread of the first 25% of the data. The box portion, so the box here, is illustrating the spread of 50% of the data. So half of the data falls in the range from Q1 to Q3. The median is a reference point for which 50% of the data is either less than or greater than. So there's our median in this case. And finally, the right-hand whisker illustrates the spread of 25% of the data. So in this case, that's representing how much the top 25% of the data is spread out. Just a quick reminder of the definitions here for skew. When you have the leg going out to this side, when you got the long side from the median out to the side, that tells us that it's right skewed or positively skewed. When you have the long leg going out the other way from the median, then that's left skewed because it's going to the left. And when there's not really a significant difference, when the median is more or less in between, directly in the middle of Q1 and Q3, then we say it is symmetrical or has no skew. Let's look at an example now where we're comparing things. We've got the speed limits in 3 different European cities. We've got Stockholm, Vienna, and Brussels. We can see, remember, all of them have the same speed limit of 50 kilometers an hour. In Stockholm, The median is coming in at about 38. The maximum is just barely at 51, so it's just barely over the speed limit. The minimum is way down at 28, and the first quartile is at 33, and the third quartile looks like it's 47.5. Overall, it looks like Sweden is a very law-abiding group of people when it comes to speed limits. Or maybe they've got really heavy traffic and they just can't drive fast enough. I don't know. In Vienna, we see that the median is just a little over 50 kilometers an hour, so the Austrians seem to have a slightly heavy foot. The maximum is way up at 63. The minimum is down at 37, and then we've got our Q1s and our Q3s. What's probably worth noting now at this point is if we compare Vienna and Brussels. We've got the median here, and the median in Brussels is right on 50. So exactly half the people in Brussels are going above the speed limit, and exactly half are going below. But it's really not that different from Vienna. The median is just slightly over the speed limit. The range in Austria is a little bit less. It's a little bit smaller. Here you have a higher maximum and a lower minimum in Brussels. But overall, the behavior of drivers in those two cities are fairly similar, but they're significantly different from Stockholm. So on average, drivers in Stockholm drive more slowly than those in Vienna and Brussels. We could also say that more than 25%, but less than 50% of Stockholm drivers drive at a slower speed than other drivers in Vienna and Brussels. The median in Vienna is above 50, illustrating more than half the drivers do not obey the speed limit. And the spread of data for Vienna and Brussels is relatively similar, with Brussels having a slightly wider range than Vienna. And almost all drivers in Stockholm obey the speed limit. With a median of 37 and a Q3 of around 47, more than 75% of drivers drive at a speed under the speed limit. Let's try a couple more practice problems. These are a little more complicated. It says the number of days off taken by employees in a company during a 2-year period was recorded. The data was organized into a box and whisker diagram as shown below. So it says the number of days off range from 5 to 46. We've got a Q3 of 13, a Q1 of 13 and a Q3 of 30, and a median of 25. We're asked that for this data, write down the maximum number of days off for employees taken during the 2 years. So the maximum is 46. The median is right there, and that's 25. And the interquartile range is from 30 to 13. So we subtract that, and we get an IQR of 17. Now it says Stephen claims that this box and whisker diagram can be used to infer that the percentage of employees who took between 14 and 30 days off is greater than the percentage of employees who took 25 days or more. Is Stephen correct or not? So let's think about this. Looking at the 25 days or more, first of all, that's saying from here all the way out to there. So that's the 25 days or more. Well, 25 days or more is going directly from the median out to the maximum value. By definition, that is 50% of the data. So going from there to there, that's 50%. He's looking at from 14 to 30 days, so he's just a little bit inside the Q1 and right to the Q3. So we're going from there over to here. Well, we know that going from Q1 to Q3 is also 50%. So in this case, he's excluded a little bit of this section here, and by excluding that, this amount that he's chosen is actually less than 50% of the data. So we would have to say it is not correct to say that those who took between 14 and 30 days off is greater than the percentage of employees who took more than 25, because in fact it is slightly less. This next problem takes a little more thinking. We're told that a research student weighed lizard eggs in grams and recorded the results. The following box and whisker diagram shows a summary of the results where L and U are the lower and upper quartiles respectively. The interquartile range is 20 grams, and there are no outliers in the results. Those are both very important facts for solving this problem. The first question says, find the minimum possible value for U. My first reaction is, well, I don't know, we didn't get enough information to do this. But in fact, they did give us some information. When they tell us the interquartile range is 20 grams and there are no outliers, we can use that information. So we know the interquartile range is 20. And we also know that that's equal to Q3 minus Q1. Because we're told that there are no outliers, we know that both the lower and the upper data points are within the fences. So that means that 75 is less than or equal to Q3 plus 1.5 times the interquartile range. Right? If you think about that, this number is not an outlier, so it has to be less than this, because anything bigger than that number is going to be an outlier, and we're told there are no outliers. So now we can go ahead and kind of evaluate this. We can say less than or equal to Q3 plus 1.5 times the interquartile range was 1.5 times 20. So that is Q3 plus 30. Now we want to get just the Q3 all by itself. So we're going to subtract 30 from both sides. We'll have 75 minus 30 is less than or equal to Q3. 75 minus 30 is 45. So we know that Q3, also known as U in this case, must be greater than or equal to 45, right? We can turn this around. So Q3 is greater than or equal to 45. That's great. What about now finding, how do we find the value of L, which we know is Q1? How are we going to find that? Well, because we know what the interquartile range is, and we know the formula for interquartile range, we can take now our newly found number here for Q3 is 45. We can say that 20 is equal to Q3 minus Q1. That's 45 minus whatever Q1 is. To get rid of the 45, we're going to subtract it from both sides. So we end up with 20 minus 45, which gives us negative 25. And we've got negative Q1 on this side. We need to multiply both sides by negative 1 so that we end up with Q1 is equal to 25. So by using the information that we're given, we can find that the minimum possible value for the Q3 would be 45, and then as a result, the minimum possible value for L would be 25. Now it's your turn. Try the homework.